Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Sri College of Engineering. I'll be talking about backpropagation, which is most important topic in deep learning, and it is also the main building block of deep learning. And before going to see the backpropagation, and we should understand what is gradient descent algorithm. It is going to be a first order iterative method. If you look at any optimization technique, whether we will work on a minimization problem or maximization problem, okay. So if you look at the graph, this is a point, this is the initial weight, and we wanted to update the weight and to have a minimum cost feature. So when we move in the opposite direction of the gradient, okay, that is in additive gradient. These optimizers are used to change the attributes of neural network, that is weight and bias. Okay, so to reduce the loss, what we should do is we should move in the opposite direction to the gradient of the loss. This is a function with respect to loss, with respect to weight, and we want to find out the new updated weight that is equal to the old one minus learning rate and partial derivative of this loss with respect to weight. So in order to have a small change, and we should not have the weight update should not be more than the old weight. So that is the reason it is the negative. Since it's a minimization problem, we have given the negative sign over here, and the learning rate is also going to be very, very small. Okay. So how this partial derivative is going to be calculated? It is going to be calculated based on change rule. Okay. So if you want, this is a neuron, and this is the error function over here, and the output function is there. The error function is the dou L by dou Z. So if you want to find out the loss with respect to x, we can calculate by the dou L by dou Z and dou Z by dou X. The dou Z by dou X is a local gradient, and this comes from the previous layer. Okay, so this is the way it works. This is the way we update the weights in the neural network. So what is happening in neural network? Then what we do is what we do in the feed-forward network is we randomly choose the weights and bias, and once we get the output, and if the error is too much, error is large, and we should update the weights, and the updated weights are going to be based on the gradient descent algorithm. Okay, so once we get the output, and we update the weights of each layers. So that is the main fund of backpropagation. To understand how these weights are being updated, and we should look at an important numerical problem. Okay, so basically we have input layer, and we have hidden layer, and we have output layer. Okay, so in hidden layer we have 3 neurons, and in output layer we have only 1 neuron. Okay, so this is the function is this is the linear function. This is going to be a sigmoid function is applied in hidden layer, and here we apply this Tinax function. So this is given the problem. Okay, so the weights, the corresponding weights between the input and hidden layer is represented by V, and hidden to output is represented by domain. Okay, so this is our initial weight is given, and the actual output is 0.15. These two are I1, I2 are basically input features, input values, 0.5 and minus 0.4. Okay. First, what I said was the backpropagation is we have to calculate the forward propagation, and then once we calculate the error, and we can go for the backpropagation. In case of input layer, it is linear one, and whatever the value we have got, it is passed to the neuron. That is 0.5 and 0.4. Okay. So then if you look at the input of different neurons in the hidden layer, it is all getting summed up. Okay. So if you look at the first neuron, first input, first neuron of the including hidden layer is Hi1. Okay. Hi1 is the input of the first neuron. Okay. So from where he is getting, and it is from the input 1 and input 2, and the corresponding weights are given over here. So we can calculate for the all three neurons in the hidden layer. Okay. So once it all getting summed up, and we have to activate that. So in the activation hidden layer, we use sigmoid functions. When you use sigmoid function, these are the values that we get. Okay. So then output of the input layer is from the all three neurons, all three neurons from the hidden layer. Okay. So we have the weight for the each one, and finally we can get this 0.19824 is the O input in O I1, that is input of the input of the output layer. Okay. So we want to find out O1, that is output of the output layer. Output of the output layer is this tonnage functions. If you apply all the, if you put this value over here, we get the 0.19563. So the error can be calculated based on this formula of target minus predicted one. Okay. So then based on this formula, we can able to calculate this is the error that we got in the feed forward calculations. So what we have to do is we have to minimize the errors. How we minimize the error, and we have to apply that gradient descent algorithms. Okay. So the change in weight is going to be this one. That is here we earlier said the change in weight is going to be earlier we said W nu is equal to W old minus eta and change in loss with respect to weight. Okay. So the old we will come to the left hand side of the equation, and this is going to be W11. Okay. So how we can calculate this change in weight with respect to this is equal to minus eta dou E by dou W11. Okay. So this is our error. This is going to be the error of this one, and with respect we have to update the weight of W11. Okay. So how we can do this, and that is the error divided by dou O1 and dou O1 divided by dou I1 dou I1 divided by OW11. Okay. So this comes from the chain rule. Okay. So first part of this one is this one. This one we have to calculate. How we can calculate this? We can calculate based on the earlier expressions. What is this? That one. This is going to be dou E divided by dou O1 is equal to off into, we have written off into target minus predicted whole square. Okay. If you differentiate, okay, so you will end up with this. Okay. Similarly, we can do for dou O1 divided by dou I1. That is in output. This is input. Okay. And when you do this, and when you do the tanh function, then you will end up with this. And what are the value you have butterfly, you will get the gradient value. And similarly, we can calculate for this one category. So dou I1 is basically this one. Dou I1 is basically this one, and dou I1 is a summation of W11 and this one, this or activation from the first neuron, and W2 is activation function of this one, and the W31 is 31 into this activation function. What are the output of this third neuron in the hidden layer? Okay. So since we divide by dou I1 divided by dou I1 is equal to H1. Okay. So we know all these things. And if we apply, then we can able to find out this dou E by dou W11. Okay. So this is a value we get. Okay. When you apply here, with respect to the learning criteria he is given in the problem, we will be able to calculate the dou del W11. Okay. So similarly, we can calculate for other change in weights. This one we have calculated, and in the problem, and this too can be calculated based on this way. Okay. So once we calculate this for the hidden to output, and we have to update the weights of this all 6 weights. Okay. So similar expression can be similarly we can calculate of all the cases, and this is the value we get from the uh, from the network. Okay, so these are the updated weights and these are the updated weights for the case of input to hidden, and these are the updated weights for the case of hidden to output layer. Okay, so this is a way we can update the weights in the back propagation network.